Hi, today I'm going to talk about a problem that can occur when you do a material model calibration, and that's related to local minima in the fitness function. So I have an example here. This is a chloroprene rubber that I tested in uniaxial compression, and I have a material model that I'm working on that I want to calibrate to this data. And this is a little bit made up, but the point here is to show you the issue that can occur. So I used run once with this set of parameters shown here, and I get the blue curve here. The blue curve is kind of in the middle. The error is 14.4% here. What I'm going to do now is I want to calibrate this parameter, and I'm going to say I want to calibrate only these two parameters, mu and tau base, and maybe even just tau base. I'm going to calibrate to tau base only. So I'm going to calibrate this using a gradient-based approach. I'm looking at the quasi-Newton method, which is searching in the gradient direction for this calibration. And if I run this, and I've done this a few times, it just doesn't converge at all. It doesn't improve the predictions over this particular value. So it's easy to understand, though, that this can't be the best solution. If I, instead of having tau base equal to 4, I make it, say, 0.5, and I run this, the error is lower. It's 12.6 now. So the solution we got with a gradient-based search approach does not give us the best answer. And what is causing this? Well, it's the nature of the material model function and the errors to come out of it. So let's take a look at a parametric study. So here is a parametric study. I kept everything the same except the tau base value. And I tried a few of them in M calibration, and I also recorded the error value on the right column here. And as you can see, a tau base value of 4 gives you exactly the same error value as a tau base of 3 or a tau base of 2 and anything in between here. So if you're trying to calculate it numerically, the derivative or the gradient of the error function, so you can search for tau base, the error is flat. So you can't use a gradient-based approach if you start over here and try to search a minimum. You see, this is the error function. There is a minimum over here, but it's really hard to find that using the slope of this curve. And this is just one parameter to search for. In real life, of course, we have many parameters we search for, and this is more difficult to visualize this effect. The point is, though, that there is a local minimum, it's a better minimum down here, but you can't find it from over here using a gradient approach. You would have to be much closer to where you want to be for the gradient approach to work, and then that would solve this problem. So how do we overcome this issue? In M calibration, what you need to do, there's two choices, right? One difficult and one easy. The difficult choice is to manually adjust these parameters, or have the software, which actually tries to do this for you, find initial guesses of the parameters to bring you close to where you want to be so that the gradient-based approach will work. The other choice to do is to simply use a different material model calibration. I don't typically use the quasi-Newton or, say, the Levenberg-McHardt method. These are gradient type methods. Instead, I use one of the extensive automatic method that has a little bit more randomness to it. It searches over a bigger space of parameters. And if I really have a poor guess, I sometimes switch over to the CMA-ES method, which is more of a global optimization method. So here is an example. It's really surprising almost that the error function is flat, completely flat in this example with respect to one parameter. So that makes the calibration challenging. But there are ways to get around that, and these are the methods that I would use in this case. Hope you found this useful. If you have any questions, you can ask them below.